Hello and welcome back. In today's video, we are going to learn about no slip condition, which is very important in case of fluid mechanics. Very important condition. This is basically a boundary condition that's very important to start with the entire subject. Now, what we are going to cover in this video is the definition of what is no slip condition. Then fluid property which is responsible for this condition, four important consequences of the boundary of this no slip condition, four important consequences, very important. Then what is flow separation, and where is no slip condition applicable based on this flow separation, and finally what is temperature jump condition, which is similar to this no slip condition. So let us start. Now, what is no slip condition? We know if, for example, this is fluid flowing and it suppose a rock, a stone comes in front of this flowing fluid. What happens is, as we know, this fluid will never flow through this rock, that will not happen. So what does that mean? When this fluid approaches at this point, suppose, or let's make it simple, when this fluid approaches at this very point, since it does not go through the rock, which means velocity normal to the surface Vn is 0. This is definitely 0. So this is we are observing this. So since this fluid cannot pass through the rock or this object which is impermeable to the fluid, it cannot pass through, which clearly means the velocity that is normal to the solid surface is 0. This is from observation, and we can observe this. So all of us can observe this. Now, number 2 point is that now we know this fluid will go around this rock or this object, but what we can't know is the fluid layer which is adjacent to the solid surface, just adjacent to the solid surface. So what is not clear is what happens to that fluid layer. So one thing that we are sure about is when the fluid comes to 90 degrees to this surface, the fluid layer which is attached to this solid surface, the normal component of the velocity will definitely be 0. But now question arises, what if the fluid comes, the layer that has to remain attached, or that has to come in contact with the solid surface, if that fluid surface does not come at 90 degree angle to the surface, but comes at some angle, say theta. When this fluid comes in contact with the solid surface at an angle theta, we will have two components for this. One will be the normal component to the surface, this V normal. So this will be velocity of the fluid that is coming in contact with the solid surface, and it will have this tangential component like this, which is parallel to the surface, V tangential. So we know normal component of the velocity has to be 0, because the fluid does not pass through this solid surface, impermeable solid surface. But does the fluid which is in contact with the solid surface move tangentially to the surface? That is the important question. If fluid solely comes normal to the surface, so it stops. Since it does not go through this solid impermeable solid surface, Vn is 0, or the total velocity is 0, because the total velocity is composed of normal velocity only. But if the fluid comes at some angle, it will when it comes in contact with the solid surface, it will have both components, normal and tangential. Normal, we know from the same experience that normal component will be 0, but does tangential component also become 0 when the fluid surface come in contact with the solid surface? Now all experimental investigations show that tangential component also becomes 0 for the fluid surface that comes in contact with the solid surface. Now this concludes that whenever fluid comes in contact with any solid surface which is impermeable to the fluid, the total velocity of that layer which is in contact with the solid surface is 0. This has been called as no slip condition. No slip condition, meaning the fluid layer in contact with the solid surface does not slip. It does not slip in the normal direction. It does not slip in the tangential direction. No slip occurs. It just stays at rest in contact with the solid surface. Since no slip occurs, it's called a no slip condition. That means no normal velocity component of the fluid layer and no tangential component of the fluid layer. That fluid layer which is in contact with the solid surface, not all other fluid layers. Fluid layer in contact with the solid surface, there will be other fluid layers are there. We are not talking about those layers. We are talking about only the layer in contact with the solid surface. Total velocity becomes 0. This condition has been called as no slip condition. Now fluid property responsible for this. Now fluid property that is responsible for this complete stop of the fluid which is in contact with the solid surface is viscosity, denoted by lower Greek letter mu. Now if we talk about an ideal fluid which does not have any viscosity, which is inviscid, there will be no fluid layer in contact with the solid surface that has 0 velocity. It will definitely have velocity. It will definitely move because it's ideal fluid. It will have a tangential component. Forget about, suppose if it is impermeable, it will still not have normal component, but it will definitely have tangential component if it has a 0 viscosity. So the fluid property responsible for this complete stop of the fluid layer in contact with the solid surface is viscosity of the fluid. Now 4 important consequences, very important part. Now 4 important consequences of the no slip condition start with this. Suppose this is fluid coming at some velocity v, and we have a suppose flat plate which is about to come in contact with this free flowing fluid which called free stream. So fluid coming with some velocity, say v, not in contact with any solid surface. This is called free stream. Now when this free stream comes in contact with this parallel flat plate, what happens is at this point, beyond this point, at the left of this starting point, what will happen is that the velocity will be same vertically like this. So this is just before coming in contact with the solid surface. So velocity at this point will be of this magnitude. At this point it will be of the same magnitude. At every point velocity will be of the same magnitude, and that magnitude is this v. See, so if we draw a line at the tip, this becomes the line that is parallel to this reference line, indicating velocity at every point is same. We call this uniform velocity. This is uniform velocity, same at every point. Now after it comes in contact with the solid surface, what will happen? Suppose this reference line this black reference line, we're going to move here. What will happen now, because of this no slip condition, the fluid layer in contact with this solid will have zero velocity. That means I will not draw any arrow, because drawing any arrow means if I draw an arrow of small length, which means it will have the layer that's in contact with the solid surface will have some magnitude of velocity. But since velocity is completely zero, so this will be totally a point, not an arrow. Now the layer which is just above this layer will have small velocity. Layer which is above that will have more velocity. Layer above that will have larger velocity than this. Above this will have larger velocity than this, because one fluid layer attracts the another fluid layer with force of cohesion, that we know, intermolecular force of cohesion. So since when this bottommost layer comes in contact with the solid surface, it completely stops. When it completely stops, the above it will attract the layer above it and decrease its speed. That will attract the layer above it because of the cohesion and decrease its speed. But as we move away from the solid surface, the above layers will have larger velocity. The velocity will go on increasing, and if we go towards the solid surface, the velocity go on decreasing, and ultimately will become zero for the lowermost layer. So here velocity will be zero, and here at the top the velocity will be whatever the velocity was maximum, this whatever the velocity was for this free stream. And we see that the first consequence of this no slip condition is that instead of this normal velocity profile, we get this. So this shows us this velocity increases as we go away from the solid surface, and this curve is called a velocity profile. So first consequence of this no slip condition is development of velocity profile, and velocity profile gets developed. For free stream it was uniform, now it becomes a special shaped velocity curve called velocity profile. So first consequence, velocity profile is developed. Now second consequence of this is velocity gradients get created. Velocity gradient. Now what is gradient? In short, gradient means when something changes with length. When something changes with length, we call it gradient. If pressure changes with length, pressure gradient. Temperature changes with length, along any length, temperature gradient. Velocity gradient in the same way. Since here velocity is zero and here velocity is maximum, in between, while going from this point to that point, velocity changes with what length? With this vertical direction. Let's call it y direction, and this is the flow direction, the direction in which the fluid is flowing. Let's call it x direction. Now here what happens? Velocity changes along y direction. So velocity becomes function of y. So velocity changes along the normal direction. That means we get normal velocity gradient, denoted as du divided by dy. It is change of velocity with respect to y direction. It is zero, it is increasing and becoming maximum. So the second consequence of the no slip condition is that the normal velocity gradient gets created. And third consequence is boundary layer is formed. Now what is boundary layer? Now since fluid is coming here from this side, suppose this is the fluid that is flowing. Now this entire free stream of fluid gets divided into two types of regions. One region, this, and a second region or other region beyond this. Now this region is something like this. The layer attached to the solid surface is completely at rest. The above layer has some small velocity because it is attached to the layer which is completely at rest, it will have smallest velocity. Then this layer, it will have velocity greater than this. Then these layers. Ultimately, when we reach to the layer whose velocity is 99% of the free stream velocity. Whose velocity is 99% of the free stream velocity. So this is the fluid layer. This is the fluid layer whose velocity is 99% of the incoming velocity. That means the layers beyond that will have velocity completely equal to the free stream velocity. But as we go below this line, below this layer, the velocity will decrease. It will decrease, and ultimately become zero at this point. Now, this region of flow in which velocity gradients exist, we call it boundary layer. Boundary layer, because beyond that, velocity gradient does not exist. Velocity will still be uniform type. Beyond that, it will be like this uniform type, having profile uniform and having value same as v. So this region is called a boundary layer, and that region will be non-boundary layer, that will be outside this boundary layer. So third consequence of no slip condition is the development of boundary layer, which is very important. And the fourth consequence of no slip condition is surface drag. Surface drag, also known as skin friction drag. Skin friction drag. What is this? Now, since fluid comes in complete rest with the solid surface, and all other layers are attached with each other, what will happen is that this fluid, since it gets stick with the solid surface, so when the fluid moves in this direction, because of this stick, the bulk fluid motion will have a consequence that will drag the plate in the flow direction. So it's like a sticky fluid flowing, gets stick to the solid surface and dragging it with it. So because of this no slip condition, drag force is applied on this solid surface in the direction of the fluid. So this fluid will have tendency to drag this surface of the plate towards its flow direction. We call that drag as surface drag or skin friction drag. These are four important consequences of the no slip condition, which is velocity profile gets developed, velocity gradients exist, boundary layer is formed, and surface drag is applied. Now, flow separation and applicability of no slip condition. Now, if this solid surface were not flat, but suppose it were rounded, like fluid flowing over a cylinder, so what will happen? The fluid layer in contact with this round surface will have zero velocity, and fluid moving forward will remain attached to the solid surface. If the fluid is moving with very low Reynolds number, very low speed, it will remain attached. But if the fluid is moving at some higher velocity, what will happen? This boundary layer, the layer that gets static, what will happen is, and the layers in which the velocity gradient exists, this entire boundary layer, what will happen? If the Reynolds number is slow, if the fluid is moving at low speed, this boundary layer will remain attached to the solid surface all the time. But if the Reynolds number is high, if the flow is moving some higher velocity, what will happen? At some point on this curvature, this boundary layer will get separated from the solid surface. It will get separated from the solid surface. Total separation occurs. This point where this separation occurs is called a separation point. And this phenomenon of this boundary layer getting separated from the solid surface is called flow separation. This is the separated region over here, the empty gap between the flow and the solid surface. Now this flow separation occurs. Now validity of our no slip condition. We assume that the boundary no slip condition is applicable before separation at all points as well as after separation at all points, this no slip condition is also valid, which is very important, which is a subtle point, but it is very important. Now, no temperature jump condition. Now, in the similar manner, we can take the argument to temperature from velocity, and we can say that this fluid, which is initially at some velocity, suppose T naught, and suppose this solid surface is at some temperature T surface. Now, when this fluid comes in contact with this solid surface, the layer of the fluid that is in contact with the solid surface will have, suppose, temperature T naught. Suppose T naught is lesser than T surface, it is at higher temperature than this. So the fluid layer that is in contact with the solid surface, what will happen? Heat transfer will occur. Heat will transfer from solid surface to this fluid until the two layers, that means the lowermost layer of the fluid and the uppermost layer of the solid surface, they will achieve the same temperature because of this zero law of thermodynamics. They are in contact with each other, they will achieve that, they will assume the same temperature, they will have the same temperature. This in the same manner, like this, it had velocity v, solid surface was at rest. Now fluid layer which came in contact with the solid surface assumed that zero velocity, assumed the velocity of the solid surface. In the same manner, it comes at temperature T naught, comes in contact with the solid surface. The solid surface has temperature Ts. This fluid will assume the temperature of Ts. So that means no temperature change occurs from its top layer and the fluid's bottom layer. They will have same temperature. We call it no temperature jump condition. That means the lowermost layer and the solid surface will have same temperature. It is same concept as the no slip condition. So this was all about no slip condition and its important consequences, and a similar condition in heat transfer was no temperature jump condition, which similarly develops a boundary layer which is called the temperature boundary layer, and this is called, in order to differentiate it from temperature boundary layer, we call it velocity boundary layer. That will be all for today's video. Thank you.